Welcome, Dr. Samantha, to this course. And now I hand over for further your talk.
Very much for the kind introduction. So I'm sharing the slides. Is it visible?
Yes, sir, it is visual.
So I'm starting. So today I'll give a basic lecture on the fundamentals. Just one moment.
Sir, your voice, I
Yes,
think
I just stopped. Is it audible now?
now audible. Perfect,
Okay,
sir.
so I'm just arranging the laser pointer. So
Sure.
So today I'll talk about the fundamental of sensor technology and how the basic sensor technology, the classical sensor technology, can be converted to the quantum sensing technology, and what are the basics of the sensor normal or the classical sensor technology, and if we convert those technology to the quantum sensing, how the improvement can be done. And in parallel on to that, we will discuss how the sensitivity, not only the sensitivity, the other parameter of the sensor technology can be improved using the quantum measurement. So those can be discussed together. So first we have to know where we are using the quantum, the basic sensor technology. So the outlines of my talk is I'll first introduce the sensor technology, and then we'll discuss about the basics of sensor technology, and then I'll give some example of the conventional sensor technology, and then I'll discuss the limitations of these classical sensors and sensor technologies. And I'll discuss about the importance of the quantum sensing and their impact on the improvement of the various parameters of the sensors. And then I'll discuss some of the key quantum sensing technology. Specifically, I'll focus on the standardizations of the physical measurement quantity, specifically the electrical measurement, how we can improve the electrical measurement like the current, voltage, capacitance, resistance, how it could be improved by introducing the quantum technology or quantum sensing, and those I'll discuss, and some of the effect of those types of fundamental quantum sensor on the biological sensing also. So those should be discussed, and then I'll finally give a comparison table related to the classical and the quantum sensing, and then I'll summarize the futures of this technology, where we are standing now and how it could be improved in future, and how much work needed to do the practical use of those the new upcoming quantum sensor for the futures. So if you think that nowadays we are using the sensor almost everywhere. So sensor are using the metrology. Metrology means the measurement quantity we are using the day-to-day life in our operations of the mobiles, calculations, laptop operation, those and the standard measurements we needed in the SI units. We use the metrological sensor. And nowadays, IoT is also the very important part, where we are connecting these sensors to the observable digital communications and digital imagings. Those are impactful in our day-to-day life. Healthcare is another important factor where we are using those sensors. And other things we can say the environment. So environment study is very important, and now we are getting more updated to the climate changes, day-to-day changes, and those can be improved or getting accurate information we are getting from the use of the lot of sensors. And the futures we can see the industrial development 4.0, that is the AI and the robotics could improve the technological evolution. Those can be useful in day-to-day our improvement of the industrial standard, can be useful for using sensors. So in details, if we want to focus one by one those sensors, then we can focus on the one of the fundamental sensors can be useful in the quantum the sensor metrological improvement. So sensors generally act as an interface between the physical world and the digital information system. They provide quantitative inputs for control system, AI models, and scientific experiment. Core role is for this sensor is to establish traceability of the SI unit in the metrological standard. So those can be useful for our day-to-day the standard measurement of SI unit. We are using sensors. The IoT is is another important applications of the sensors. So nowadays the billions of interconnected devices are in the we are using in the day-to-day devices, where we are using low power and the miniature sensor. Basically, we can see some of the examples like the MEMS accelerometer, gyroscope, which are also used in the smartphone to enable the motion tracking or the algorithmic AR and VR, like the visual reality, can be useful using the sensor and the navigation system. So nowadays, the market of the IoT is rapidly increasing, and it could surpass the $1 trillion in the year of 2030. So you can understand the impactfulness of the IoT, use of the sensor in the IoT in the future, present and the future market. So another important factor is the healthcare and the biomedical field. So in that case, we use the sensors, which we call the biosensors. Those biosensors are various types of biosensors which are useful, and we are using day-to-day, like the glucose monitoring system, wearable ECG or EEG patches we are using to the detections of our electrocardiograph signal, and several others application. And day-to-day also more sensors technology are coming to point of care detection. So other techniques also, the sensors also couple the MRI, CT scans, and other new coming quantum-based biological sensing. Those will improve the diagnostics, early diagnostics case, and the improvement in the improvement in our cureness, early cureness of the disease. So other impactful effect of these sensors are the environment and study and the energy applications. Sensors are nowadays used for purifications of the airs, and also the quality measurements of the air can also be done by various sensors, which can detect water quality monitoring, soil monitoring are also the very important in our day-to-day life, and which could be use several type of the sensors. And so, and also nowadays, smart grids employ current and voltage sensor for real-time monitoring, enhancing the renewable energy integrations to the smart grid. So other things are the automations in the weather stations using multi-sensor fusions technology that could improve the climate change monitoring. So those the predictions of the climate change can be done with a better accuracy by using multi-sensor fusions. And the others is the major sector are defense sector, aerospace, space sector, and also the navigations. They use several types of sensor to inertial measurement units to get the GPS-based navigation system and so on. So you can understand that the sensor can be useful for almost everywhere. So these sensors are very, very important nowadays in our day-to-day life. So now, what are the major problem in the classical sensors? If we consider the classical sensor in brief, I can say that the classical sensor limit by thermal noise, electrical noise, and some calibrations related drip, and those can restrict our sensor limitations. So the advantage of the quantum sensing, which explore the quantum states like the superpositions, entanglement, and the squeeze states, which will be I'll discuss later in details. That will improve the quantum sense. The sensor can be improved by using this quantum principle, and they can improve the standard the quantum limit to the towards the Heisenberg limit. So where if we consider the standard quantum limit in the uncertainty in the any measurement, which is in general proportional to 1 over square root of the n, when it is the number of the independent particle during the measurement. So this will give you the limit. The scaling is if you consider this the standard quantum limit, which is given by inversely proportional to square root of n due to the Poissonier's Sartenoid related phenomena that I'll discuss also in later. Just basic thing we can consider that this is limited by the noise phenomena, and you can get the limit of the accuracy in the measurement of the order of this factor. But in case of in case of the Heisenberg limit, where you can so in the Heisenberg limit, we have to the limit of the measurement or the accuracy in the measurement is proportional to 1 by n. So it provides better better understanding or the accuracy in the measurement and for example, if we give the intense photon state in an interferometer, can detect phase shift with the sensitivity scaling as 1 by n, while the which is far sharper than the classical limit of 1 by root n. So this can improve the limit of the accuracy in the measurement, and when we go for the not classical system towards the quantum system. So now the factor is that why it's important in sensing. So in practical term, this HL Hygienic means fewer resources to do the precision measurement, or equivalently, we can say the much higher sensitivity is possible for the same number of particles. So if you consider that to detect the accuracy of the classical way, you need the measurement of let's 1,000 particle, where you can get the better accuracy, even just simple 10 number of particles. So that can be improved. Lesser number of particles can be used to get the better accuracy in the measurement. Major applications, if we look into for the quantum sensor, that could be the gravitational wave detections. So in gravitational detection, LIGO employs switch light states to push below the SQL limit, and it's going towards the HL limit. Another example or the applications of this quantum sensor is the atomic clock, where Intel's atoms can be used to reduce the uncertainty in the frequency measurement. Other measurement is the quantum magnetometer. But quantum magnetometer can measure the high precision measurement of the magnetic field, and in example for those can be used by the NV center, that is the nitrogen vacancy center in the diamond. So you can use, it's a deep states, a combined deep level states of nitrogen in the diamond and the associated vacancy, carbon vacancy in diamond. Those combined system can be used to detect a quantum correlation system, quantum correlated system, and to accurately measure the magnetic field in the level of femtotesla. So of the order of 10 to the power minus 15 Tesla, you can accurately measure the magnetic field. So that types of a system can be useful for the accurate measurement of the magnetic field. Other system like you can consider the electrical measurement, and it contains several things, including the current, voltage, resistance, capacitance, etc. So in the current one sensor, you can consider the quantum electrometer. So quantum electrometer is nothing but a single electron transistors which can accurately measure the single electron, and even the possible fractions of electron can also be detected by the system depending on the configuration of the system. So accurate measurement of the electron is possible. Single electron can be possible by the quantum electrometer. So another example, you can see the voltage standardization. To do the voltage standardization, this means how accurately you can measure the voltage without error. Means you can consider how precise, let's say 10 to the power more than 10 to the power minus 8 or 10 to the power minus 9 level of accuracy, you can able to measure the voltage, which is possible by using the Josephson junctions, like the superconducting Josephson junction, that could be useful for the standardizations of the voltage in coupling with the quantum electrometer like the ECT. And the other thing, the quantum resistance standard, which can be used the quantum Hall effect, which is the quantized Hall resistance, which could be useful to detect the resistance. The combinations of these three can also use to define the capacitance and capacitance in the quantum standard. So other applications you can consider that the quantum sensor can be useful even single molecule level detections of various or the small or large molecule of the biological system, and you can able to make early stage detections of any abnormality in your body. So those applications can be done with this quantum sensor, and high level accuracy can be possible. So one question come in the frequency measurement that I'll discuss in the later when I will discuss about the quantum metrological part. So that could be discussed later on. So now I'll discuss about the sensor means how these sensors can be useful. So fundamental, first you have to know the basics classical sensor. What does we mean by the sensor? A sensor is a device that detects, converts, and transduces a physical, chemical, or biological stimulus into a measurable signal, which could be like the signal could be electrical signal, optical signal, or the mechanical signal. So a sensor is a device which can check, which can convert the physical, chemical, or biological information to a physical quantity like the electrical signal, optical signal, or the mechanical signal. Those conversion device is called a sensor. So to do these sensors, we have to know the several important parameters to define a sensor is a good sensor or it's a bad sensor. So it's not only one parameter which could define the sensor is a good, very good sensor. So there are several parameters we have to check to make or to understand our fabricated sensor is a good sensor for a particular application. So we have to check the property like sensitivity. That is the most important, first important thing, that how it can sense the signal. Second is the selectivity. So how it can select two different phenomena by each other. That is the selectivity of the signal. Let's, for example, two different biomolecules, how we can selectively detect that these are two different biomolecules. So that gives you the selectivity. And then the resolutions. Resolutions is the how small amount of the physical quantity, physical or chemical or the biological quantity you can able to measure by the sensor, that give you the resolutions. And second, another important factor, the response time, how your signal you are getting, how fast you are getting the signal, so we can get the information early stage. That is the signal sensor response time. So early response is we can make the fast sensing device. So we need the response time. We need to know the how is the response time of the sensor, and then the stability of the device for the long time application. How the detection or the signal is it changes with time or not. That will give you the information of the stability of the your sensor. And then the reproducibility of the data for or the long time or multiple application, how it's give, that you have to know. So these are the important factor you have to know to understand a basic sensor. So example of the sensors are the classical sensor are, one we can say the physical sensors. One type is physical sensor, which can be the use the physical standards of the measurement, such as the temperature, pressures, force, motions, light, or the sound. Those can be useful for the physical sensors. And some examples are the piezoelectricity can be used for the piezoresistivity, thermoelectricity can be useful for sound system. For piezoelectricity or piezoresistivity can be useful for thermoelectricity, can be used for temperature measurement. Optical sensors can be used for the photon or light detections, or the different frequency range of light detection can be done for the physical sensor. And the importance you can I already explained that where it could be useful. Those are the importance of the industrial automations, IoT device, aerospace navigations, or the environmental monitoring. So these are the physical sensors. Other sensors are the chemical sensors. Chemical sensors generally detects the various chemical signal in the form of electrical, optical, or mechanical properties, and from the different types of targeted molecule that can give. And some example we can say that those are the electrochemical gas sensors, which can detect different types of gases. So not only these are the O2, CO2, H2, I say those are the basic gases. Not only day-to-day carbon, the other gases, like you can say the toxic gases, which are generally used in the semiconductor industry to fabricate these types of devices, basically our laptop or mobiles, those or we are using the computers or the next generation, the quantum devices, basically the solid state based quantum devices or other devices. We are using the various toxic gases like the phosphine, ammonia, the diborane, so other gases also. Those are toxic. We need any leakage of those gases can also be dangerous for the human beings and the others, like some gases are the flammable. So detection is important. So these types of sensor, chemical sensor, electrochemical or chemical sensor can help to early detections of any leakage, etc. So the others measure like the pH sensor or the plasmon, surface plasmons, resonance-based molecular detection. Those are the various systems which can use for the classical chemical sensor. So simply, I give one of the basic, one of the types of the chemical sensors which can be used, like the CNT, carbon nanotube types of system, where you can convert the signal of you can convert the electrical signal without any gases or biomolecule or chemical molecule. You get some signal, and with the gas molecule or the other chemical molecule, they will change, and that changing can be detected to get the signal output, and we get the presence of this gases or other chemical molecules. So that can be done. So these are important. As I say, the various applications of the sensors are the environmental monitoring, industrial process control, food safety, early disease detection. These types of sensors can be useful. So for the biological sensors are useful to detect biological molecule like enzymes or the proteins, DNA, RNA molecule, or the living cells. Those can be detected by biological sensors. So some example you can consider the glucose sensors. We are now, it's available in our day-to-day life. You can take this glucose sensor in your home and you can test it so quickly. So these types of sensors are now improve our day-to-day life. Who have basically have diagnosed these types of disease. So those sensors help us to improve our day-to-day monitoring of our health. And other is you can give the DNA chips are now in the fabrication phase. Several immunosensors are also in the process, in the development stage, or some are also in the market. So those are very useful for our day-to-day life. So what are the major importance? We can develop the point of care diagnostics device, wearable healthcare monitoring system, personalized medicines, or the biodefense system can also be useful for these types of biosensors. So now it is also the not only the one single sensors are doing the the chemical, biophysicals, or the biological sensors are separately, but nowadays also several sensors are under development or also in market to play a interdisciplinary roles, which can be give the interdisciplinary effect, like lab-on-chip devices, which integrate the physical something like the microfluidic channels. So these microfluidic channels are something like a various micro or nowadays also nanofluidic nano level micro channels are formed by the various and advanced nanotechnology they fabricated, and from that they can make all the lab experiment within this chip level, which also several chemical detections, biological detection can be performed in the lab on chip devices. So other applications nowadays, the quantum sensors or even the single quantum sensors can be useful for different applications. Let's example, if we have a single electron transistors, I'll give in the details of the single electron transistor later, which can be useful for, as I said earlier, that it could be used for the monitoring the ampere measurement or the single electron level current measurement. It can also be useful single photon detection. The same device can be useful for high ultra sensitive single molecule detection. So this new technology, that quantum technology or quantum sensor, can be useful for same device, can be useful for various interdisciplinary applications. So now I want to discuss one by one important things like the sensitivity. We have to check the sensitivity of the parameters in details. We have to understand that as I explained earlier, that the parameter to define the better performance of a sensor, which are the sensitivity, resolutions, accuracy, noise, the signal to noise ratio, etc. How we can define those things, that we have to discuss. First important thing, the sensitivity. Sensitivity is the change in the output signal per unit change in the unit signal. So if we have the quantity, output quantity is y, let's the change in the output say quantity, the signal is delta y, means y is the output signal and x is the input signal, and you change small change in the input signal, that is delta x, then your sensitivity can be measured as the delta y by delta x. So some example is the thermocouple sensitivity can be measured. The output is in terms of voltage and the input is the temperature change. So per unit change is the temperature, how the voltage can be changed. So that can be the measurement of the thermocouple sensitivity. So that so we can't determine the efficiency of this sensitivity can define that how small changes can be detected by the sensor. That will give you the measurements of how system or the sensor is sensitive to any change in your measurement. So that will give your the sensitivity of the system of the sensors or the various the sensors technologies. So another important parameter is the resolutions. Resolutions is the how we can the resolutions can give you that how smallest detectable input change the production of the measurable output. So if we say that you want to measure the resolutions can be defined as R as any small change in the measurement, this quantity of the let's smallest possible measurement quantity can't be measured by the sensor is x min. So the change in delta x minimum is divided by the full scale measurement. So this will define the resolution. So if, for example, you can see the pressure sensors have the resolutions of 0.01 bar at a full means if delta x min is around 0.1 bar and the full scale measurement you are doing the 100 bar, then the R is the 0.01 divided by 100. So the resolution is 10 to the power minus 4. And which are the resolution is limited. Resolution mainly limited by the noise, and noise is limited by the square root of kb. Kb is the Boltzmann's constant, and T is the temperature, and B is the bandwidth of that signal. So that give you the resolutions of the system. The second problem, the third one, the measurement we can do, the parameter which can do the measurement, better measurement understanding of the sensor is the accuracy. So the accuracy is the closeness of the sensor or which measured value is close to the true value. Let's you have the measured value is x measured, and your actual value is the x true. Then your accuracy of the measurement can be defined by that the mod value, difference of the measured value minus the actual value of your of the data that divided by your the true value of the measurement quantity. So if you convert it the percentage, you can get the measurement accuracy. So measurement accuracy is another important factor that you can define how closely or how error free is your measured data. So next level of the understanding of the sensor is the noise. So we need to know the noise spectral or the noise spectral density. So this noise spectrum density is the random fluctuations in the sensor output, or that is not related to your input. So whenever you measure some data, you can find that some small fluctuations is there in your the output signal, and which is not related to your input signal, and those the small fluctuations of data we call the noise, and this noise can be measured or quantified by the sparse spectral density, which can be defined as the Sn of the F is the frequency of the noise. So that could be defined as the mod value of the NF square divided by delta F, where NF is your noise amplitude after frequency of F, and delta F the change in the frequency. The other parameter is the thermal noise. Thermal noise can be defined by the Vn square, or where is it's related to the 4 kb. 4 kb is a Boltzmann's constant, TRB, where R is the resistance of the system and the B is the bandwidth, T is the temperature. So this is depend on the thermal noise of and another noise is exist in that case in many of these devices, the short noise, and this short noise is related to the quantum limit, and those noise can be defined by that the short noise can be defined as square root of 2 EIB, where E is the electronic charge, I is the average current, and B is the similar bandwidth. So this noise will how play important roles. Lower noise is better for the measurement accuracy. So the resolutions of your measurement can be defined based on your noise level of your sensors. Means if your noise level of the sensor is low, your resolutions of the system should be high. So another important factor for understanding of the sensor is the signal to noise ratio. So signal to noise ratio can be defined as the signal, what you are getting the signal output, and divide the power of the signal output or divided by the power of the noise output. So that can be defined as the 20 log 10 is the A signal is the amplitude of your output signal, and the A noise is the output of the noise signal, amplitude of the noise signal. So you can get the signal to noise. Higher the signal to noise ratio is the better or better measurement quality of your sensor. So another important parameter are the linearity. So linearity can be measured by the maximum of the actual value divided by minus the ideal value divided by full measurement scale of your parameter. And the example where it could be useful is the definitions of the strain gauge measurement, where the linearity is important. Deviations from the linearity will deviate your accuracy in the measurement. Another the parameter we can use is the dynamic range measurement. Dynamic range measurement can be the defined how the signal is moving with the minimum detectable. The maximum measurable signal can be measured with respect to the minimum detectable signal, and can be defined by this way, where x max is your maximum your measurable signal, and r is the resolution. So this sensor will the dynamic measurements of sensing and the sorry, 1 minute. This dynamic measurement range can help you to detect the range of your or the measurement of your sensors. And these are when if we consider this effect in the limit in the classical signal. Specifically, this limits the classical signal is more the thermal noise and the short noise, which both are the more disturbing for your sensing of the classical sensors. And if this noise can be improved by use of the quantum sensors, and it will boost the signal to noise ratio in case of a quantum sensors. So now, if we want to give the conventional example of sensors, few examples I will give, but there are several sensors which are useful or under use in our day-to-day life. One of the sensor can be the MEMS-based accelerometer, which use the MEMS technology to detect the accelerations of system. One example, this is one of the example I'm just giving, where the sensors can be. There are several new types of sensors. So simply we can use, in this case, we can use the Newton's law of force is the mass into acceleration, and any displacement in the mass due to the change in the sensors or the MEMS, if happen, that could be detected by this force change. And if we know this change, and we can check the change in the capacitance of the MEMS, and this capacitance modification can be detected by this MEMS sensors, and we can get the information of from this system. So the applications are the airbag systems, smartphones, robotics, and vibration analysis. Those MEMS acceleration are now useful. Simple other examples of the physical sensors are the photodiode. Simply, I can say the one of the examples is the photodiode, where you have the diode characteristics without any photons. When photons fall, additional electron hole pair will be generated due to the interaction of the material. Maybe we can consider the band-to-band electron hole pair generations, and that will change your the current level, and those current change due to the photon fall on the diode, that can be detected, and you can get the photo detection. So this is the simple one types of photo detectors can be used. Several new types of photo detectors are in research level, which are FET-based photo detector, and nowadays I'll give you some examples of the ACT-based photo detector. The ACT-based photo detectors are actual your quantum photo detector. So those can be those are in the research level. And the several example of the biosensors, if we say, there are various biosensors which could be the biosensor can be based on the bioreceptor based system, based of transducer based system, or the based on the different types of nanotechnology. Using the some example can be the SRP, means the plasmonic surface plasmon resonance based system, or various optical based, and so on. So several sensors are in research level, and some are in our day-to-day life. So now if we want to know that these are the classical sensors which are useful and have some limitations. So what are those limitations of the classical sensor? First limitations is the noise. So noise introduce random fluctuations in sensor signal. Fundamentally, they limit the measurement of resolutions. So how many types of noise are there? First noise is the thermal noise. So thermal noise, basically known as Johnson-Nyquist noise, and that can be measured as the root mean square of noise voltage, and that can be defined as the Vn square equal to 4 kBT RB, and I just explained earlier also that the noise measurement root mean square noise voltage can be defined by this formula, where kBT is the Boltzmann's constant, T is the temperature, R is the resistance of the system, and B is the bandwidth. So another the noise is the short noise. This is the coming from it's a classical noise, but coming from the quantizations of the current flow, and that can be defined as that square root of 2 into electronic charge. I is the current, and B is the bandwidth of the noise. Another noise is called the flicker noise, which is commonly known as the 1/f noise. And those 1/f noise are generally originated at very low frequency, and which can be defined as the the square root of, it's proportional to 1 inverse f to the power alpha, and this alpha value is generally varies system to system. It can vary in the range of 0.5 to 2 range. So this noise can't limit your the sensing of sensitivity or the resolutions or the other parameters of the classical sensor, which we just described. So these are the major problem in the classical sensors. The next problem which will arise in the classical sensor is the drift and calibrations issue in the system. So drift is happening due to offset. Some offset will happen during your measurement. Specifically, if you say that with time, you want to measure some quantity, let's say V0, and you are getting some V output with some variations of your time. So you measure some, want to measure this one, and some output you are getting this one. Due to the variations in time, some delay or higher or some parameter will be there that will deviate your actual measurement, and that the coefficients of this deviation with respect to your parameter are it's called the drift coefficient. So you are not getting with time, you are not getting your or the measurement value in a same level. So this drift will happen during your continuous measurement of your sensors. Other is the major effect is the temperature drift. So if any variation in temperature happen during your measurement, and your measurement quantity will change. So your reference temperature with respect to temperature, and you have some deviations in temperature, so that will modify your measurement with respect to a temperature coefficients of alpha. And so this modification always be there. Even you simply consider you are using a diode for any signal detection. So you continuously use the diode, the electron hole pair, more electron hole pair will be generated, and this more electron hole pair during the transport will generate more Joule effect. So those Joule effect will heat up the system, and your temperature of your measure reference from the reference, it will slightly be higher. When it's higher, then your deviation in the measurement will happen. So that temperature drift can happen in your during the measurement. So that shift is impact your sensitivity in your classical sensors. The other parameter, another important parameter is the sensitivity thresholds of the sensitivity threshold of the classical sensors, which can be defined by the minimum detectable sensor, which is actually how minimum signal can be detected. That could be defined by sensitivity threshold, and that can be defined by the X min, and which is equal to the noise in RMS over the sensitivity of the of your sensors. So where NRMS is the root mean square noise. So large the noise, your sensitivity minimum detectable signal level will be reduced. So that is the important factor. So it basically it's a sensor give your sensor capability to detect a weak signal. So your signal sensor is capable to detect the small signal of your or change over your measurement quantity is possible or not. That could defined by your sensitivity threshold, and this is very much important. It depends on your or the noise level of your sensors. So you can understand that classical sensors have limits in detections, although you can get better sensitivity by comparing the classical knowledge, but we cannot go beyond a certain limit, and those limits can be crossed by the quantum sensor. So quantum sensors, what is quantum sensors? So quantum sensors or quantum sensing is the use of quantum states of matter or light. Such the quantum states of matter or light, something like you can consider superpositions of the states, entangements of the state, and the squinching of the quantum states will helpful to define the physical quantity, and which will give the high precision measurement of your quantity which want to sense. So these quantum sensors can cross the standard quantum limit by exploring towards it can go towards the Heisenberg limits, and using the major quantum phenomena like the first thing is the superpositions. So, but that we all know that the quantum state can exist in the multiple states simultaneously. If let's assume two states, 0 and 1, and it can anywhere 0 and 1, and with some probability of alpha in 0 states, and the beta is the probability, the coefficients of that coefficients of that the staying in the one level. And any comment?
And Dr. Aru,
Yes.
if needed, we can have a 5-minute break, and then you can continue.
Okay. I don't have any problem. So if the students or the audience needs the break, I can provide. I don't have any issue. So now I will enter the quantum, real quantum system.
Okay, I think please continue.
So and just 1 minute. So in quantum sensors can use three important properties of the quantum mechanics. That first one is the superpositions of the system, and the second one is the entangements of the states, which we can define that the quantum particle become correlated to that they are the different states, and they are inseparable to each other. So if the 0, 1, the initial the two states, and if we say the degenerate states are 0 and 1, and they can exist as the combined states, which is 1 over root 2 of 0, 1 plus the 1, 0 states. So that okay. So some audience need some break. So I am giving on the 5 minutes break.
Okay, thank you, sir. Thank you.